I think this is something like my 18th day of teaching myself C++. So I want to talk about some of the optimizations or the optimal ways of using standard vector and some of the things you should avoid doing. So for this, I will, let's just include our IO stream and include vector. And we'll have our main function just return 0 for now. And for this demonstration, I want to create a class, and we'll call this data. And inside data, we're basically, this is just a demonstration of how some of these things work. So inside of this class, I'll just store a string of text, which we'll call text. And we'll set it to default text for now. And we also need to import string. The other thing we need to do is create a constructor. So we want to, when we create an object, a data object, we want to be able to pass in a string of text. So we can use what's called a parameterized constructor. So the way we do that is we create a function with the same name as the class, and this will take in as input a standard string, which we can call text as well. And inside of this, when this constructor function is called, when we're creating a new data object, what we need to do is set the value of its internal text variable to be equal to the string of text that we passed in. So basically when we create a, for example, if we create a data object, we'll just call it D. We can call the constructor by using this syntax and then pass in a string of text like my text. And what happens is this says inaccessible. I think I need to put a semicolon here. Oh, we need to make this public. These are public methods. I guess we can make this a private. That would make more sense for this to be private. All right, so there we go. So back to what I was saying. When we create a object called D and we pass in this input text called my text, it basically creates a new object, a data object, and then it sets that new object's internal variable called text underscore to be what we passed in here instead of the default text. Similar to that, if we wanted to have the default constructor, we could have just this. Well, I think we can do something like this, where basically if we are creating an object without passing in an input, so if it was just like this, then the object created through the default constructor will have just the default text. So that default text is not being replaced by the input text because there is no input text. So hopefully that makes sense. And one small optimization we can make here is in our parameterized constructor, instead of actually explicitly setting the value of the internal variable like this, there's something called the member initialization list. And what this does is it's able to set the value of our member variables before even calling this function, which I think in this case would have to trigger like a move or copy operation to reset the value of this, which was already initialized. And it would have to change that to be the value that we input. But instead of doing it this way, the member initialization list allows us to directly set the value of our internal member variable text like this. So the syntax is after this parentheses, there's a colon, and then the name of the internal variable you want to set, parentheses, the value that you want to set this member variable to. And then you can remove what's inside of the curly braces here. So if I did this correctly, this achieves the same thing as what I had before, but it's slightly more efficient because we don't have to do a move/copy operation to reset the value of this variable. So now I will talk about some of the behaviors of standard vector. Maybe I can just create a standard vector here, and it will hold data objects. And we'll just call it something like logs or something like that. So this is me creating an empty vector that will hold data objects, and the name of it is called logs. And for this demonstration, I want to count the number of times that our main function both initializes and copies our data objects. So the way we can track initializations is, this is not good practice, but I'll just create a global variable of integer called initialize count, and we'll set its value equal to 0 by default. And in our constructors, basically, whenever the constructor is called, that is when a new object is being initialized. So instead of this default constructor, I can use the standard style of constructor, and we can just increment the initialize count variable. And I think I have a typo here. Initialize count. So in this constructor, we can just increment that count. And the same thing we can do in our parameterized constructor. So basically what's happening here is every time that we create a new data object, our global count should increment by 1. And I can demonstrate that here. So we can print out to the console number of initializations, and then our variable, and then just a new line character. And since we're not initializing any data objects for now, we're just creating a vector, this should be 0. So if we compile, let's run g++ standard vector.cpp, output standard vector, and we can run standard vector. So that's what we expect, is there are 0 initializations. But if we were to create a object, a data object, we'll call it text, like this. This will be calling the default constructor, which is this function here. So we would expect that our initialize count should go up by 1 because we're creating 1 new data object. And if we run it, we do see that there is 1 initialization. The other thing I want to track is the number of times that our data objects are copied within our program. So one thing that I don't think I've talked about is called the copy constructor. So this is another type of constructor. And this constructor, the way that we write a copy constructor is like this. So it will be also have the same name as the class, but this time the input will be a reference to a data object that is called other. And inside of the constructor, we're going to set the member variable called text equal to the value of the other object's text variable. So this is a little bit hard to conceptualize if you're not familiar with object-oriented programming, but basically this other keyword is referring to another object of the same type of data. So it's a data object. And in this case, what that other object is the object that we are copying from. So when this constructor is called, we're creating a new data object, and then we're setting the value of the new object's text variable to be the value of the object that we're copying from, that object's old text variable. Okay, so if that didn't make sense, you can probably look up more about copy constructors. But for now, I will also make a global variable called copy count, set it equal to 0 at first. And then in this copy constructor, we can increment copy count. And then we can also print the number of copies that we're making. And I think that in this function, we should be performing 0 copies. So let's check that. Yep, so we're still just initializing 1 piece of data, and we're not doing any copies. For our copy constructor, we also can use the member initialization list instead of this syntax. So I will do that now. We can also just set the value of text to be other.text here, and we don't have to do that in the body of the function. Okay, so far everything is behaving as expected, and now I want to just show what happens when we are using standard vector in a pretty common way. So one thing that we might want to be doing is we have a vector of logs of data objects. So we might want to be pushing in some number of logs, right? So we can push data to the logs vector like with the method pushback. And inside of this method, we'll pass in the data that we want to push. So we'll create a new data object, and we can pass in some sample text into its constructor. And so what happens here is we are just adding this as the first element in the vector since it was initially empty. And if we print out what happens now, oh, I forgot to put increment here. Some of you guys were probably yelling at your screen about that. But now if we print out what happens, we get 1 initialization and 1 copy. So why do we see a copy here when all we're doing is pushing a piece of data into our vector? let me draw a diagram about what's happening here. So basically what's happening here is when we call this constructor here, when we're creating this data object, we're passing in the sample text into this parameterized constructor. What happens is that this data object that is created in this context is actually being allocated on the stack. So this sample text object is temporarily being created on the stack. And then what happens when we push this this object to our vector is that it must copy this object into the heap. And this is actually quite an expensive operation for large data objects. So maybe with a string, it's not so bad. But if you can imagine that you had some other object that stored much more data, you actually would have to have 2x the space, like the memory, in order to copy, because the object exists both on the stack and the heap at the same time while it's being copied. So this part makes sense. And I want to show also what happens when we push back multiple elements to the vector. So if I create 2 more objects and I push them to the vector, maybe let's create 4 objects. So we're doing the same thing here. We're just pushing 4 objects to the same logs vector. We can also check how many initializations and copies. Okay, so we see that 4 initializations take place, which is logical because there's 4 objects that we're creating. But now we see that the number of copies is 7. So you might have thought that based on what I just showed in the diagram, we would have to have just copied once for each of these objects that we're creating on the stack and then pushing over to the heap or into the vector. But actually what's happening is with dynamic arrays, I can make another drawing again. The issue is that when we create this vector called logs, it's actually initialized to just being an empty array on the heap. And the size of this initial array is fixed because of the way that arrays need to be stored in contiguous memory. They actually can't grow in size. So what actually happens when we push a single element to this array, that's fine because there's space for one object. When we want to push another element, there's actually no room in this array. So the way that vector works in C++ is that it's a dynamic array. And what that means is that instead of being able to expand this initial array and have room for another element, what has to happen is that a new memory address is allocated. And this new memory address actually has enough room for 2 of our objects. So depending on the compiler, I believe the way that the arrays expand is different. I think in G++ it actually just doubles in size once you reach capacity. Basically, when we created this element and we wanted to the second element and we wanted to add it to our current vector, we had to allocate some new memory and then copy the contents of this old vector into the new vector and then add the value of the new element into this new array. And you can imagine, since we pushed 4 elements, there's now this new size 2 array is full. We had to double it once again. So we would allocate maybe 4 spaces for the next array. This would have to be copied over once. This would have to be copied over a second time, and then 2 more elements needed to be pushed in. That's probably why we're seeing so many copies just with adding 4 elements to our vector. So one way to actually avoid this is there is a vector method or function called reserve. So we can use logs.reserve. And this is telling the compiler the size of the vector that we want to create. So in cases where we know the number of elements that we need to be storing in our vector, we can tell the compiler that we want to reserve a certain number of spaces for those elements. So in this case, if I know that there's going to be 4 elements in my logs vector, we can reserve 4 spaces in that array. And what we should see when we run this again is that we can see that there are less copies being made. So this is probably the result we would have expected based on the first example. And what's happening in this case is that each one of these 4 elements needs to be created on the stack and then copied over to the heap one time. So that's a pretty cool and simple optimization we can use. As long as we're able to know the size of our vector beforehand, we can use reserve to preset the maximum size of that vector, and we can avoid the unnecessary copies. But like I mentioned before, copying is actually a very expensive process because it both wastes CPU cycles and it requires you to have 2 copies of the memory or the data available in your memory like at the same time. So one thing that we can do to avoid copies is, instead of using the pushback method of vector, there's a method called mplaceback. And what inplaceBack does is basically, instead of creating the object on the stack and then copying it over into the heap, inplaceBack is able to create the object directly on the heap, and it avoids the copying process. And actually, we have to change what we're passing into inplaceBack to be just the contents or what you want to pass into the constructor. So instead of passing in a data object, you're passing in the value that you want to pass into the constructor. So once we do that and we run our program again, we now see that the number of copies has successfully been reduced to 0. We're still going to need to have 4 initializations, and that's something you can't avoid because we're creating 4 objects. So that's still optimal. But now using inplaceBack instead of pushback, we're able to reduce the number of copies from 4 to 0, which is a pretty good improvement. One thing to be careful of when using inplaceBack is that even though it looks like we've eliminated the copy operations, there's actually still a way for it to be doing something not so efficient. And in order to show that, I need to create what's called the move constructor. So right now we already have 3 different constructors, but this 4th one will be the move constructor. And the way that this is created is with a double ampersand. And we also need to use this keyword no except. And to be honest, this is beyond my current understanding, so you guys can look up move constructors, but I'm just copying what I've seen in a textbook. And what we can do is a move operation. And also let's create a counter for moves. And I think we need to import memory for our move operation. So essentially what this is doing is similar to the copy constructor. It's instructing for whenever this object needs to be moved in memory. It's giving instructions for what needs to happen. To be honest, I'm not really sure how to explain what's going on here. So again, I would look it up in a different video or online. But this is giving the data object instructions for when it needs to be moved rather than copied. Move is a little bit more of an efficient operation than a copy, since you don't have to have like 2 copies of the data in memory at the same time. Just for the sake of example, I'm also going to have a move count incrementer here, same as our other constructors here. And again, we can actually use the member initialization list instead of having this in the body of the function. So let's do that here like this. We can set text equal to standard move other.text. I think we can remove this. And I have a syntax error for somewhere. Maybe we have to put this over here. Yeah, I think that's correct. Okay, so this is now our move constructor. And if we log the number of moves that we're performing, I'm going to change this back to the way we had it before, where we're passing in this text as into the constructor. Okay, this is just purely to show that the syntax is important here. So if we run this again, we actually see that we are still getting 4 initializations, which again is unavoidable because we're creating 4 objects. We have successfully reduced the number of copies to 0, but in the background, what we didn't see is that when using this sort of syntax with inplaceBack, the program still has to perform 4 moves. The reason this is happening is the same as before, and basically when we're using this constructor, we're still creating this data object on the stack, and this data still needs to be moved over to the heap. And since we have now supplied the class with a move constructor, instead of performing a copy, it's able to use this move constructor's instructions and move the data over instead of copying it. So this is slightly more performant than performing a copy, but it is still not optimal because we need to move data from the stack over to the heap. And we're performing basically unnecessary CPU cycles to create the object on the stack, move it over, and then pop it off the stack. So the way to avoid these moves is if we use inplaceBack the proper way, which is instead of passing in objects to the function, we just pass in the parameters or the input arguments that we want to pass into the constructor. And now hopefully if we have this all correct, we can see that we now have 4 initializations, 0 copies, and 0 moves, which I believe is pretty optimal for this sort of use case. So what's happening here is instead of mplaceBack creating an object on the stack and then having to move it over to the heap, when we pass in these function parameters directly, mplaceBack is actually able to allocate this object directly on the heap instead of on the stack, and this saves us these expensive move and copy operations. So this is what I came up with for a visual demonstration. And basically, imagine that these two folders represent my stack and heap memory. And if we open up both of them, so the stack is on the right and the heap is on the left. When we're creating vectors and pushing elements over to the vector using pushback, you can think of it like we're creating objects on the stack. So we can create like maybe 5 objects. So what's happening is we have to create these 5 objects on the stack. And then when we're using pushback, we need to copy these 5 objects over to the heap. And then finally, these need to be popped off the stack. And now you have your objects stored in your vector on the heap. But as you can see, that took quite a few operations, right? So one of the optimizations we added was instead of having to copy them, we can just move them using mplaceBack. So that would look like if we had a number of objects, they're still created on the stack, but instead of having to copy them over, we can just move them directly. So they're instantly popped off the stack, and we don't have to have 2 copies of the same data on both the heap and the stack. And the final optimization, which was using reserve, mplaceBack, and the move constructor, we can avoid the allocation on the stack entirely, and we just create the new objects directly on the heap, and they're immediately stored in our vector in the heap. So that we don't have to do the copy and paste and then the delete, and we don't have to create them on the stack first and then move them over. They're just immediately created on the stack. So that's pretty much it. I just wanted to share what I've been learning about vectors in C++. And if that helped any of you guys, please leave a comment, like, and subscribe, and see you in the next video.